Okay, once more, I've already posted a correction, but this is the projection of F13 on F12, the projection of this vector onto this vector, and this is the way we write it: projection onto F12 of the vector F13. I had the 1,3 here and the 1,2 here previously. I was careless in writing down 2s and 3s. I did the same here. This is a 2. Okay, well, now we've got an expression. This part of the expression gives you the length of this side with a positive if theta is less than 90 degrees, with a negative if theta is greater than 90 degrees. Be sure you understand why. It's simply right here that by the definition, or by this relationship for the dot product, the magnitude of F13 cosine theta, which is what we're looking for here, is going to be this divided by the magnitude of F12. And that's multiplied by the F12 vector divided by the magnitude of that same vector. Often a textbook, usually a textbook, will give you this formula with the F12 squared down here. And there's nothing really wrong with that if all you're going to do is follow a formula. But if you're going to understand and reinforce your understanding of this picture, which is, I think, essential for properly utilizing and conceiving of a projection and the use of the dot product and finding the projection, I don't think you want that F12 squared there until you're very comfortable understanding how to develop this formula from this picture. So I'm not going to use a PAP formula with an F12 squared in the denominator. I think it's a very bad idea at this stage. So anyhow, we're going to calculate now this projection of the F13 vector on the F12 vector. I'll also mention there's no good reason usually to project one force vector on another, although there could well be, and actually we'll see one. But it's not something you usually do. But there are many cases where you do project one vector on another, and we might as well, since we're using these examples, we're going to go ahead and go through the process, which is actually quite simple once you understand all this. Excuse me. And then we'll look at least one example of where we would project a force vector onto a displacement vector and get a very meaningful result. Okay, well, so our F12 vector is here, F13. We've seen all this. F12 dot F13 is 20 newtons squared. Magnitude of F12 is 12 newtons. Magnitude of F13, 7.5 newtons. So this part of the vector, which again gives us this side of the triangle, but with a negative if theta is greater than 90 degrees, is just going to be what? It's going to be 20 newtons squared divided by 12 newtons. And that's going to be multiplied by the F12 vector over F12. And I've actually calculated that over here. I guess I'm going to go ahead and write it out in this form. 8.0 newtons, 8.9 newtons vector over the magnitude of the vector, and the magnitude of the F12 vector is again 12 newtons. And that gives us 20 newtons squared over 12 newtons is 1 2/3, 1.67 approximately. And that's going to be 1.67 newtons. If we do these divisions, well, we've actually already done them previously, and I've quoted the result here, but that's the vector, 0.67, 0.74, and let's go ahead and put a boundary in here, okay? And then we simply multiply this out, and we get the projection. And multiplying that out, we get, and it's very straightforward to multiply this out, we get 1.12 newtons, 1.24 newtons. And if we resolve that, take the arctangent of 124 over 112, we get 48 degrees, just a little less than 48 degrees, and we get 1.67 newtons. Not exactly because of round off, but it does round to 1.67 newtons as it should. And you'll recall that we talked about where this all comes from. If this is 77 degrees, then this component here is 7.5 newtons times the cosine of 77 degrees. And we multiply that by the unit vector in the direction of F12, which was 0.67, 0.74. And if we do that, we get something very close to this. Actually, the magnitude of this is going to be more like 1.69, and the angle will still be 48 degrees, and that's just due to the round off error on the angles and on the components of the unit vector. And I've indicated this is the same as this within round off, and you should understand this picture and what it's telling you and why it ought to be exactly the same as this picture. That's a fairly good chunk of understanding, but that's what you need at this level. And I'll also mention that this is very, very important in your vector calculus course, which most people coming into a university physics course are taking. So this will do double duty for you. Very important picture, one of the central pictures in the early part of multivariable or vector calculus. However, this is also something that's done in a good, rigorous pre-calculus course. So this should have been part of your preparation to date. For most of you, it probably isn't, because you didn't have a pre-calculus course at the level that one would hope a good student would get, simply because perhaps we try to teach that part of pre-calculus to too many people. Not following your instructors, they have to pass people.